Welcome back to the Professors DuBois channel. I am Professor Victoria and this is Professor Corey, and today we're going to be talking about gas-forming reactions. We've already talked about precipitation reactions and acid-base, and today we're going to be talking about gas-forming.
All right, gas-forming reactions. These are one of my favorites, and the reason I really like these is they give something visible, something you can see. It's like, oh, I know I have a reaction, because when you have a gas-forming reaction, you see bubbles. And a common one you might have seen, I don't know, these antacid tablets. I mean, they were...
If you had an upset tum-tum, you might have had an antacid tablet.
Yeah, I don't know if people use these anymore, but you put this tablet in water and it fizzes like crazy. And so we know there's a reaction occurring, and we can see these bubbles. So this is a good indication or proof or evidence, I should say, that there's a reaction going on. So it's a special type of reaction.
Right. So we've already talked about how we can predict the products of our reactions, and you're going to be doing that as well for the gas-forming reactions. So when you perform a reaction and you look at the products, you can see if there's a gas. And these are some things that you need to look for. So if you see hydrogen or oxygen or chlorine or fluorine, the ones that you know are gases already, those other diatomic elements.
Yeah.
But you might not have known H2S, certainly carbon dioxide, right? That's a gas, we know that. SO2 as well, so you can kind of remember that because CO2 and then SO2, sulfur is right underneath carbon in the periodic table, and they behave similarly.
Similar family.
Right. Also NH3. So ammonia is a gas, and these are all gases at room temperature. So if you see one of these as a product, you know that's a gas, and you know it's a gas-forming reaction.
So for right now, I think what I would do is write these down and have them handy. And with a little bit of practice, you'll be able to identify these without having to reference your notes. But these would be good to write down.
Yeah. So you can see in our example here, we have a double replacement reaction. So we have let me get my pen, we have our sodium. Recall that we write our ions up here, not the number of ions, but just the ions. And we can do a double replacement reaction, which means that we have the cation from one goes with the anion of the other. So that makes a 1-to-1 ratio. So we have their NaCl. And then this hydrogen then goes with the sulfur. And remember the positive ion, the cation, always is written first in the formula, but the sulfide ion has a -2, so we need H2S. And that's one of the ones that we said, hey, keep a lookout for that because that's a gas.
Yeah, so we can write little g, kind of a subscript G, to indicate that that is a gas.
Yeah, we haven't had that little subscript G yet.
And if we perform that reaction, we would see bubbles, which is really fun. Now, there's 3 compounds here that will decompose. Remember we talked about decomposition as a type of reaction? These 3 compounds will decompose very quickly if they're formed. When you do your double displacement reaction, you need to look for these, because writing these 3 compounds out as a product would be incorrect. What you need to write is the products of the decomposition. Now you'll notice each of these 3 produces a product that is a gas. So starting with the ammonium hydroxide, or the NH4OH, this decomposes to NH3, ammonia, that's on your list, and water. And water's liquid, so we put the little L by that. So we've got H2CO3 and H2SO3, very similar. The carbon and the sulfur in the same group on the periodic table. No surprise, they would behave similarly. So here's I call these like gas-forming reactions in disguise, because when you do your double replacement, you're like, oh, ammonium hydroxide, I'm good. Now you're not good. You got one more step, and you did form a gas.
Yeah. So ultimately, what we're going to be able to do is to give you 2 reactants. You will then perform the reaction, predict the products, predict the states of matter, and this is part of it. So another thing to write down those things to look for. Hey, these are gases, but write these 3 down as well. That's really important to know that they will decompose.
For sure.
So let's show you some actual examples with these after we show you these. So we have a couple more examples of gas-forming reactions, and we have some hydrogen-forming reactions. And our group 1 metals, when they get in touch with just water. So these group 1 metals don't actually exist in nature as themselves, because any interaction with water at all, they will react and become a compound. So they really want to be in a compound, much more so than just being a solid. But when this is a single replacement reaction, and to know that, I want you to write HOH for your water. And this breaks apart into the H plus and the OH minus. And then we know that potassium is a metal. Metal will replace the metal in the compound. So it kicks the hydrogen out and it exists as hydrogen gas. So there's 2 of them have to be kicked out and then it forms the hydrogen gas. And then the potassium dances with the OH minus. So it's in a compound with OH minus, and that is a gas forming reaction because we kicked out the hydrogen gas.
Now your potassium hydroxide is written as aqueous, and you would know that's aqueous by going to your solubility rule chart.
Right.
So we'd look up the hydroxide ion to see if that was soluble or not, and look for the exceptions.
Correct. So zinc again is a metal. So it will displace the metal in that ionic, well, it's actually, this is a covalent compound, but it can dissociate into its ions.
It's a strong acid. Of
H plus and Cl minus. So it displaces that hydrogen, kicks it off as hydrogen gas, and we have 2 chlorides for every 1 zinc because zinc is a plus 2 when it's in a compound. So we have zinc chloride there.
And again, we'd go to the solubility chart to determine the state as aqueous.
Right. Now we'll practice.
Yeah, so, okay, we've got, wow, what's this mean? Metal carbonate. Well, a metal carbonate is a metal with the carbonate. So this says metal carbonate salts react with acids to form the corresponding metal salt, water, and carbon dioxide gas. So let's see what this looks like. And maybe that metal carbonate, maybe that's something that'll stick in your mind. You'll be like, hey, that's a metal carbonate and that's an acid. And maybe not. But if it does, that's almost like a shortcut. But we're going to do this the long way. So we're going to draw our ions up at the top. We're going to switch the cations. I like to just say switch the cations. So the calcium is now going to go with the chlorine. Or the chloride ion. I need 2 of those to make a neutral compound. I go to my solubility chart, and that is an aqueous. That would be aqueous in water.
Soluble, yeah.
Now I've got my hydrogen going with the carbonate ion. So I need 2 hydrogens, and I make H2CO3. Now, this is where you might think
you're done.
You're done, and you're not. This is one of those 3 compounds that decomposes very quickly. So a lot of times you'll write it. You won't even, you'll write it, and I think it's fair to write it and then just put a line through it and write CO2 and water. And just recall that the CO2 is a gas and water is a liquid. And I mean, that shows really good understanding. I formed this, which then decomposed. That's a good way to write that one.
I agree.
So be on the lookout for those. They can really be a problem when you're working on homework assignments and stuff, if you miss that.
Right. Let's try again. H plus and Cl minus, those are the ions that HCl would break apart into. Lithium is just +1. Sulfite is a -2.
So again, we got, this generic metal sulfites with acids. That's just a clue. It's not critical that you remember that, but if that stuck out to you, that it would be like a shortcut. You'd know right away, oh, this is gonna be trouble. So H2SO3, and I'm done.
No, you're not. All acids are soluble. That's why I'm writing this AQ there. But it is one of our gas-forming decomposers. So we do not make that. I want black here. It makes, just like it before, it was CO2. Now it's SO2 gas.
And water is a liquid.
And Water's a liquid, pure substance. It's not aqueous. It's not water dissolved in water.
Right.
And we're not quite balanced. I think I need a 2.
Oh, nice. I didn't even look to the others and should have.
In front of that.
Yeah.
Good.
What do we got here? We got the ammonia forming reaction. So we've got a ammonium. Is that ammonium chloride? It is.
Sorry.
We're just going to break that apart into its ions. We're going to do a double displacement reaction here. So the sodium hydroxide has a sodium ion, has the cation. We're going to switch those cations. The sodium's going to go with the chloride ion to form sodium chloride. I can look that up in my solubility rules and realize that that's aqueous, and I've got NH4OH. Now I could go to my solubility rules and I could look up this hydroxide, and I could be misled because this is not an ionic compound. Remember that solubility rules chart?
No, it is, because we have an ammonium
you're right.
polyatomic
You're right.
with a hydroxide polyatomic.
You're right. That is.
Yeah.
I saw all the non-metals and got thrown.
Right. And it is aqueous. It is soluble, but when it's in water, it does not stick around.
This is one of those decomposers. And this one's going to make the ammonia gas, and you'll smell it. Ammonia's got a very distinct odor.
Yeah.
And the reason we're smelling it is because it's in the gas phase.
You'd smell that hydrogen sulfite gas too.
Yeah, that smells terrible. Now, something worth noting: you might see a bottle of ammonia, right? Or like a glass cleaner that says with ammonia. And what they're doing is they're like bubbling this gas through the water or the liquid. The glass cleaner is probably water based. And so a certain amount of that will dissolve in the...
You can dissolve gases in water, just like your carbonated beverages.
But just like the carbonated beverage, that gas will escape. And ammonia's got quite an odor. We're very sensitive to it. So you'll smell that.
Mm-hmm. Here's your practice. All right, we've given you 3 examples here. We want you to do a double replacement or a single replacement and predict the products. So this might take you a little bit. You're going to have to pause the video and really try this. Don't just look at the answers. Really try it. It's going to help you. Do your double or single replacement. Predict your products. Make sure that you make a neutral compound. Balance it. Then look at each product and think about the states of matter. So if it's an ionic compound, you're going to have to look at your solubility table. If it's not, you might have to think about, is it one of those gases that we formed, like carbon dioxide, sulfur dioxide, hydrogen gas?
Right.
Those things.
Did you form one of the 3 decomposers? Make sure you write your the products of that decomposition as well with the states.
Yeah. Here comes the answers. There they are. That bottom one was a little bit tricky to balance, wasn't it?
That looks like a balancing nightmare.
Nah, it wasn't really a nightmare, but it was tricky. It took a little bit of time. So that's your gas forming reaction lecture. Hopefully that was helpful. Thanks for joining us.
Yeah. We'll see you next time
On the Professors DuBois channel.